In the previous video, we took a complex circuit and reduced it in order to find the equivalent resistance. In the end, we drew this simple series circuit that you see right here, and we found that the equivalent resistance of the circuit was 6 kiloohms. In this video, we're going to go backwards through our circuit diagrams in order to create a VIR chart showing the voltage, current, and resistance of each resistor in our original circuit. In order to do so, we need to start with our simplest circuit and do a VIR chart for this simple circuit. In addition to the VI and R columns in my VIR chart, I'm going to include a final column that has the letters of my resistors to help me track which resistors are in my initial circuit and which resistors are kind of a combination. So you notice that I've put A, B, C, D, and E in there. And I'm going to keep these in kiloohms in my chart. When I'm doing the math, I need to make sure that I'm paying attention to the fact that it's kiloohms, not ohms. Remember, I put my totals in that last row across. So I know this is a 12-volt battery, and I know my equivalent resistance is 6 kiloohms. We're using Ohm's law, that equation V equals IR, or that current is V divided by R. And we have 12 volts divided by 6 kiloohms, or 6,000 ohms. That's going to give us a current of 0.002 amps. Now I could also write this as 2 milliamps using that conversion factor. And I'm going to do that just because it's a little bit less writing. You are welcome to write out 0.002 amps in your chart, or you're also welcome to write out your resistance in ohms rather than kiloohms. Since this is a series circuit, I know the current through every resistor is the same. So I can fill in this chart with 2 milliamps, or 0.002 amps for each of my resistors. And then we know we can use Ohm's law to calculate the voltage in each one. Again, paying attention to units. So we get 2 volts, 4 volts, and 6 volts. Since this is a series circuit, we can do our check that those voltages all add up to the voltage of the battery following Kirchhoff's loop rule. And in this case, 2 plus 4 plus 6 does equal 12. So we're in good shape there. Once we have finished our VIR chart for our simplest circuit, we're then going to move on to the one that we drew right before that, which I have on the bottom half of my screen here. So we're going to do a new VIR chart here. Excuse me. Some of those quantities in this VIR chart we already know, and so we'll just fill them in. And we'll have to fill in our unknowns. So this time I have resistors A, B, C, D, and E. And I'll still use that final row for my totals. I know A is 1 kiloohm, BC is 3 kiloohms, D is 6 kiloohms, and E is 3 kiloohms. My total, we said, was 6 kiloohms. My total is still 2 milliamps and 12 volts. Since resistor A was in my previous chart, I can just copy those values right on over. Same thing with resistor E. I can copy those values that I had in my previous chart onto my new VIR chart. But B, C, and D were combined in my previous diagram. When I look at this newest diagram, I see that these two resistors right here are in parallel with each other. And that's what I did. In that previous video, I said B, C, and D were in parallel, and I combined them to create BCD. Since they are in parallel, we know that they're going to have the same voltage. And we know that as an electron travels through this portion of my circuit from right here to right here, it must go through a potential difference of 4 volts, no matter which path it takes. Therefore, the voltage of BC and the voltage of D are both 4 volts. Since I know voltage and I know resistance, I can calculate current. For BC, that current is 1.33 milliamps. And for D, we get 0.67 milliamps, or 4/3 and 4/6. Again, feel free to write those out as 0.00133 or 0.00067 amps. One thing to note is that it is no longer a simple circuit. Therefore, I can no longer add up the voltages to get the total voltage of the battery. That only works on a simple series circuit, remember. Now that I have all the quantities filled out in this VIR chart, I'm going to go back to my original diagram and do my final VIR chart for this one. Much like that last time, some of those quantities are the same, and so we'll just be able to write them out. Every resistor is by itself now. It was still the same circuit electrically, so it still has the same voltage, the same total current, and the same total resistance. And this is 1 kilo ohms. B and C are both 1.5 kilo ohms. D is 6 kilo ohms and E is 3 kilo ohms. Resistors A, D, and E were in our previous chart, so we can just copy those values right on over. So 2 volts and 2 milliamps for A. D had 4 volts and 0.67 milliamps. And E was 6 volts and 2 milliamps. So the only things we need to figure out are B and C, which were these two resistors up here. When we initially combined those resistors to create the diagram that we last studied, we said that those two resistors were in series, and we happen to know that current is constant in a series circuit. So whatever current was traveling through resistor BC is also the current that's traveling through both B and C. So that's 1.33 milliamps. Once we know that current, we can find the voltage, and it just so happens that the voltage is 2 volts for both of these. So this is our final chart, but we can do some checks to make sure that our numbers make sense. Those checks include using Kirchhoff's rules, so the junction rule and the loop rule. Thinking about the junction rule, there's a junction right here. So that current entering the junction, which was the current that was going through resistor A, should equal the current leaving the junction, which is the current that went through resistors B and C, as well as the current going through resistor D. So if I add up the current through B and C, that 1.33, and that current through D, that 0.67, I should get the current through A. I do, so I'm in good shape there. The other thing that I can use to analyze, make sure my numbers make sense, is the loop rule. So any loop I travel around this circuit, I should end up getting that the voltage of the battery is equal to the voltage dropped through those resistors. So one loop would be going through A, through D, and then through E. And so if I look at the voltage of A plus the voltage of D plus the voltage of E, I should come up with 12 volts, and I do. And then another loop that I can traverse around my circuit would go through A, through BC, and then through E. So if I add up the voltage of A, B, C, and E, I should also get 12 volts, and I do. So that's a good check to make sure that the numbers in your final VIR chart make sense.